Howdy, y'all. So what we got next is 8.9. So we're going to have a generalization of Young's inequality for the first part of it, where you've got supposition. And so we're going to suppose that we have P, Q, and R between 1 and infinity. And we get that the reciprocal of P plus the reciprocal of Q is equal to R inverse plus 1. So they're almost conjugate exponents, right? And R is the remainder, right? It's how much is left over when we how far off of conjugate exponents we are. So Young's inequality in the generalized form is going to give us a relation when we have almost conjugate exponents. So obviously Young's inequality is going to be a special case of this one. And then we have parts 2 and 3. Parts 2 and 3 are going to be a little bit weird. So in the same way that Young's inequality wasn't really provable with what we've done so far in class, the generalized version is even more so that way. However, for 2 and 3, we don't have the terminology necessary to even state them. So we're going to take a quick side note after we look at 1 to discuss something called distribution functions. So Young's generalized inequality, we're going to let F be in LP, G in LQ. Then we get the convolution is in LR, and we get this generalized version of the inequality. So we now have that that R convolution G of in the R norm is less than or equal to the P norm of F, Q norm of G. Okay. Now for part 2, we're going to suppose that P and Q are both greater than 1, and that R is less than infinity. So we're going to still keep F in LP. However, we're going to weaken the condition on F. So on G, we're going to have it live in something called weak LQ. Now, for this, we're going to need distribution functions. So what we have here is a distribution function. Let F be measurable on X, then lambda F from the open interval from 0 to infinity to the closed interval from 0 to infinity, with where we define lambda sub X of alpha to equal the measure of the set of X values such that the absolute value of F is greater than alpha. So what we have is how often is F larger than some value? So as we take alpha larger, obviously this is going to drop, so it's going to be monotonic with respect to alpha. And we're going to use it to define something that almost looks like the LP norms. So we're going to define this bracket, F bracket P, is going to be defined as the supremum of alpha to the P, then the distribution function of alpha. So and then we take the P through thing. So instead of actually taking the integral, raising the function to some value and taking the integral, we're going to multiply how often is it over a certain point times that level to the P, which is going to be something, as you can see, that would have that has a relation to when the integral is finite. So this is going to be closely related to the LP norm, but it's obviously a weaker condition. It's going to be a lot. So what we define in the weak LP is going to be the set of functions when F bracket P is finite. So obviously, if the integral converges, then this thing here also converges because it's going to be less than the integral. So we get that all of LP is in weak LP, but we also get other functions as well. So what we're going to do is we're going to weaken the restriction on it. We're going to keep the restriction the same on F. So F is still going to live in LP, but we're going to weaken the restriction on G so that it just has to live in the weak LQ space, not necessarily in the LQ space. Then what we get is that the convolution of F and G will still live in the LR space, in LR. So even though we restricted G to be weak LQ, we still get that the convolution is in LR. Then on top of that, we get a variant on Young's inequality, where we get, just like before, the R norm, F convolution G of the R norm, is less than or equal to, and then the product of these two. But now we take the bracket Q instead of the norm Q, and we end up with a constant out front. Now the constant, it turns out, is independent of F and G, right? So because it's independent of F and G, we can pick anything from LP and anything from weak LQ, and we get the same number here. So this number is only dependent on P and Q. For 3, we're going to get something similar. We're going to, instead of having P be greater than 1, we're going to make P 1, and we're going to make R and Q equal greater than 1. Then, if F lives in L1, so LP for P equals 1, and G lives in weak LQ, then the convolution still lives in weak LQ. And, because again, Q is R, so this is going to be the same thing as what we had before, where it lives in, is that right? Let me double check that, I might be wrong. Yeah, so this guy lives in weak LQ, so when we let P be smaller, we lose that it's going to still end up in, because Q is equal to R, so we can also say this. So we lose that it's in LR, but we get that it is in, but it still lands in weak LR. And we get that the bracket, that F convolution G of the bracket Q, because again, it lives in the weak one, so we can't just take the regular Q norm, or R norm, because remember R equals Q here. So we can still take, let's use R because it matches with one before. So we can't take the R norm anymore, but we can still use the bracket one. And it turns out that that is going to be less than or equal to CQ with the F of the R norm. So again, CQ is independent of F and G, and it's only dependent on Q or R, which are equivalent, because P is set equal to 1. So it's only dependent on that. So we get 3 different variants, generalizations of Young's inequality. The first one obviously looks a lot like what we've been working with, and then the other 2 use this generalization in the weak LP spaces. Okay, in the next video, we will be tackling 8.10. I will see you guys in a bit.